Okay, so lecture 9, vector space and subspaces. So define what a vector space is, give some examples, define what a vector subspace is, and give some examples. So a vector space is a collection of things. This is the definition. It's a lot of words. But basically, we have a bunch of things called vectors and a bunch of numbers called scalars. Those are usually the real numbers or the complex numbers, and you have to have the following rules. Two vectors can be added together to get another vector. A vector can be multiplied by a constant and you get another vector. So additive axioms, you have commutativity, you can have associativity, right? The order that you add things don't matter. There's a zero vector, so 0 plus v1 equals v1. And there's an inverse vector minus v, so that v plus minus v equals 0. Multiplicative axioms, the scalar 0 times a vector gives you the vector 0. The scalar 1 times a vector just gives you back the vector. The scalar minus 1 times a vector gives you the inverse vector, right? So that's this thing up here. And then you can multiply, if you have constants, you can multiply one constant times the vector and then the other constant, or you can multiply the two constants together. And then there's distributive axioms. Constants distribute over vectors and vectors distribute over constants. So it's not too bad. So vectors of length 2 form a vector space. So these are vectors. Right, 2 length 2, right, 2 coordinates. Closure, AB plus CD equals A plus C, B plus D. So I can add 2 vectors of this form and I'll get another vector of that form. The other closure was if I have a constant times a vector, how is that defined? Well, we multiply each component by that vector, by the constant, and that gives me my vector, and that's also a vector. So constant times a vector gives me a vector. Additive axioms, AB plus CD is equal to A plus C, B plus D. And we can reverse that, CD plus AB equals C plus A, D plus B. But these two things are equal, so we have commutativity of addition, right? And I'm not going to go through associativity because it's just the same thing. The 0 vector is 0, 0, and that plus any vector gives you the vector itself. The inverse to a vector AB is the vector minus A minus B. And that's the same thing as minus 1 times that vector. Multiplicative axioms, 0 times AB is 0 times A, 0 times B, which is 0, 0, so that's nice. That's a check. 1 times AB is 1 times A, 1 times B. It's all very routine checking these axioms. And so that's equal to the vector, check. C times D times a vector AB is C times the vector dA dB equals CDA CDB. But of course, that's the same thing as CD times AB. So we have the multiplicative distribution there. And then finally, C times vector AB plus, oh, shouldn't use C. We'll say vector EF equals C times the vector A plus E, B plus F, just same thing as the vectors CA plus CE, CB plus CF. But then C times AB plus C times EF equals CA, CB plus CE, CF equals CA plus CE, CB plus CF. And you can verify these are equal, so you can verify the other distributive axiom yourself. So it's a vector space, right? What it means is a collection of vectors. You can add them and get another vector. You multiply by a constant, give another vector, and multiplication and distribution behave the way they should. So vectors of length n form a vector space. Same procedure as above. You can take vectors of length n, you can add them together, get another vector of length n. You can multiply by a constant, get another vector of length n. What about 3 by 3 matrices? Well, I can take, for the closure axioms, if I take a 3 by 3 matrix and another 3 by 3 matrix and I add them together, I get another 3 by 3 matrix. So they're closed under addition. Can take a 3 by 3 matrix, multiply it by a constant, I get another 3 by 3 matrix. So close under the scalar multiplication. Do I have a 0 matrix? Yep, it's 0, 0, 0, is just zeros everywhere. So that's a vector. I've got a 0 matrix. Do I have negative matrices? Yeah, just multiply all the coordinates by -1, and that will give you inverse. Is addition associative? Yep. Is it additive? Yep. Pretty much the same. The same thing that we did for vectors will show that 3 by 3 matrices themselves are also a vector space, right? The things that can be added and multiplied by constants, and addition and multiplication behave the way you should. So lots of things are vector spaces, right? 3 by 3 matrices is a type of vector space. It doesn't have to be just these sort of formal vectors that we've defined. Set of all square matrices is not a vector space. Why not? We said that 3 by 3 square matrices is, but why not if we take all square matrices? And the problem comes with closure. A 2 by 2 matrix is square, and a 3 by 3 matrix is square, but you cannot add them together. Right? If you add those two things together, you're not allowed to add them together because they're different sizes. So all square matrices are not a vector space because addition doesn't work. Square matrices of a particular size, 3 by 3, 4 by 4, those are a vector space. So vector subspace is a collection of vectors from a vector space with these 3 properties. The 0 vector is included. The subspace is closed under addition, and the subspace is closed under scalar multiplication. So upper triangular 3 by 3 matrices. So an upper triangular 3 by 3 matrix is a matrix that's got numbers in the upper right-hand side and zeros everywhere else. So this is what I'm looking at. Is this a subspace of the vector space of all 3 by 3 matrices? Is the 0 vector of this type? Yes. Just set A, B, C equal to 0, and that gives you the 0 vector. Is this closed under addition? If I take 2 of these, and add them together, what do I get? I get 0, A plus D, B plus E, 0, 0, C plus F, 0, 0, 0. I get an upper triangular matrix. So it is closed under multiplication. And is it closed under scalar multiplication? Well, if I take a matrix of this form and multiply it by a constant, I get a matrix of that form. So it's closed under scalar multiplication. So it's a subspace, right? The big space is the set of all 3x3 matrices. This is a sub collection of them. And it's closed under addition, closed under scalar multiplication, and includes the zero vector. So this is in fact a subspace. All two-dimensional vectors with non-negative entries. So this is not a subspace. This is A, B, all vectors with A greater than or equal to 0, B greater than or equal to 0. Is a zero vector one of that? Yes, because the zero vector, if we have A equal to 0, B equal to 0, that gives me the zero vector. Is it closed under addition? If I add any two of these together, and A and C are non-negative and B and D are non-negative, then A plus C and B plus D are also non-negative. So it's closed under addition. Is it closed under scalar multiplication? And here's the problem, because -1 times AB, where A and B are positive, will give me minus A minus B. And that's not in this set. It's not a vector where both coordinates are positive or non-zero, or positive or 0. So not a subspace because it's not closed under scalar multiplication. So, and a really important example about subspaces is that the span of a set of vectors is a subspace. And in fact, what we'll see in the next lecture is that every subspace is the span of some vectors. So remember that the span of this set is all vectors, all linear combinations of those vectors. So it's all vectors of the form k1 v1 plus k2 v2 plus ... plus k n vn. Zero vector, yes, just set all the k's to 0. Okay. So the zero vector is a vector of this form because we can just set all the k's to 0 and get the zero vector. Is it closed under addition? Well, if we have one vector, say w equals some linear combination of v1 through vn, we'll call the numbers we'll go with k1 v1 plus ... plus kn vn. And if TUVW, call u, is another vector of this form, then w plus u is k1 plus m1 v1 plus ... plus k n plus mn bn. And so w plus u is a linear combination of v1 through vn, and it's also in the span because it's a linear combination, so it's closed under addition. Closed under scalar multiplication, well, let's take our vector w and we'll multiply it by some constant c, and then it becomes c times k1 times v1 plus ... plus c times kn times vn. Still a linear combination of v1 through vn, so it's closed under scalar multiplication. So that actually also is a subspace.